Hey guys, it is Burak from Bitmatrix, and in this video I'll be aiming to give you guys a broad understanding of how Bitmatrix covenants work. So Bitmatrix is a protocol for automated liquidity provision on the Liquid network, right? And the covenant design is based on non-interactive, stateful, and recursive covenants. So the covenant design is recursive in terms of the state being carried across inputs and outputs across transactions, right? And you have this spatial transaction called pool transaction, right? Where each state transition takes place. And within the pool transaction, you spend some old state and construct some new state. And the states are carried across these four covenants. So we have four different covenants because in Liquid, every UTXO can carry only one asset. And since we are dealing with four different asset types, we needed four different covenants. But all these four covenants interoperate each other and collectively spend and collectively construct it. And the correct construction is audited by the smart contract. So the first covenant is the flag covenant that carries a unique flag asset, right? A flag asset is a special type of asset with 1 unit supply and 0 precision. Think of that as an NFT, right? That is issued prior to pool creation and that is given to pool at the point of pool creation. And in Bitmatrix, you can have multiple trading pools for multiple trading pairs, and every single one of these pools are identifiable with this unique flag asset carried by the flag covenant across inputs and outputs. The second covenant is the token covenant that carries token liquidity as a pair to LBTC liquidity. And the third covenant is the LP covenant that carries LP tokens, right? In fact, a pre-mined set of LP tokens possessed by the liquidity pool. And the fourth covenant is the main covenant that carries LBTC liquidity as a pair to token liquidity. And the main covenant is the main smart contract that enforces all the rules and constraints on how you can make interactions and so forth. And you have a 1 minute gap between each state transition. And in fact, all inputs within a pool transaction are enforced to signal 1 block relative lock time, and this is to avoid some attack vectors. Apart from the covenant inputs and outputs, you have slots in between. And slot is essentially a piece of smart contract execution room, right? And that is made of 2 inputs and 2 outputs. That is responsible for an execution of smart contract, right? And the user is essentially aims to reserve one of these slots by creating a commitment transaction. So the Bitmatrix covenant is by design asynchronous and non-interactive. So that multiple users from multiple sources can also attempt to reserve one of these slots. And all these commitment outputs from commitment transactions are supplied to pool transaction after 1 minute, again to avoid some attack vectors, right? And they can all be aggregated in the pool transaction because any node on the network can do so. So the call data field in the commitment transaction is an op return, in fact, a 78-byte op return concatenated 5 items total, right? So the first 32-byte is the target flag asset ID that indicates the target asset, right, that I've pointed out earlier, right, carried by the flag covenants. And the second item is 1-byte math call that indicates the type of interaction the user is aiming with the liquidity pool. That could be either swap, liquidity addition, or liquidity removal. And the third item is a 33-byte pub key that indicates the destination pub key, right? And essentially, settlement output is where a trade result settles, and the witness program of settlement output commits to this pub key. And the second to last item is an 8-byte slippage tolerance field that indicates the slippage limits. During the contract execution, if your price goes below the slippage limits, your transaction gets reverted. So you get your money back minus transaction fees. And the last item is a 4-byte ordering fees field that indicates the amount of sats you are bidding over a fee market to reserve one of these slots. The commitment outputs in a commitment transaction are a single leaf pay to taproot constructions, right, made of two script paths. These two script paths are under the same tap leaf. And the first path says that in a success path, which means the commitment outputs are successfully supplied to pool transaction and are successfully executed. And in this case, what it says is after one confirmation, spend me in a transaction whose first input index asset ID equals to the target flag asset ID and no other conditions involved. Because as you can see, there is no checksum in here, right? Which means that this is a bit of like anyone can spend type of path, right? Anyone on the network can essentially spend this in a pool transaction, right? And that is specifically called aggregation. But we also have a timeout path in which after a certain period of time, given a valid signature for this pre-encoded pub key, you can also spend this, but the first output index asset ID should not equal to the target flag asset ID. So you can make a refund as well, but that refund has to take place in a non-pool transaction. Again, this is also to avoid some attack vectors. So the flag covenant again carries a flag asset, but the script content says that the first 5 lines says that make sure that all the 4 covenants, right, signal 1 block relative lock time. And this line says that make sure the current input index is 0, right? And the last 4 lines says that make sure all the 4 inputs come from the same previous transaction ID with this sequential order of votes. The token covenant again carries a token liquidity, and script is very simple though. Similar to what we did in commitment transaction, in the commitment outputs, the token covenants are constrained to target flag asset. And the same goes for the LP covenant, right? LP covenant is also constrained to target flag asset. The main covenant is the main contract, right? That is a very heavy, cumbersome script over 1,000 lines. I'll show that in the script wizard IDE for better demonstration. But prior to doing that, let's make a Bitmatrix swap using the web interface. So I have a Marina wallet set up with some test LBTC. So let me connect my wallet and say swap 0.01 TLBTC for 354 TLUSDT. So the Marina wallet created a funding transaction, and afterward the interface created a commitment transaction. And let's view the commitment transaction in mempool. So as you can see, this is a standard template of commitment transaction with 2 inputs and 4 outputs, and it spends the funding outputs from the funding transaction. So the first output, right, in the commitment transaction is the call data, right? It's a 78-byte push data, and the first 33 bytes is the target flag asset ID, right? That indicates the destination pool address. And the next byte is the method call, which is O1 apparently, which is swap Bitcoin to token K. And the next 33 bytes is the destination pub key, and the next 8 bytes is the slippage tolerance field, and the last 4 bytes is the ordering fee field, right? Which apparently is 1 sats that I'm offering to bid one of these slots. And the second and the third outputs are the commitment outputs, right? These are paid to taproot constructions, and the last output is the fee output. And as you can see, guys, the commitment outputs are collectively spent in a pool transaction. So this is a live example of a pool transaction, right? The first input output pair is the flag asset, right? Carrying this unique flag asset, right? And the second input output covenant is the token covenant carrying token liquidity. And you can see the amount being transitioned. And the third input output covenant is the LP covenant carrying a pre-mined set of LP tokens. And the fourth covenant is our LBTC main covenant carrying LBTC liquidity. And the script content is, as you can see, is very heavy. I'll go line by line and demonstrate and simulate the execution of this transaction in a sec. But the last two inputs are the commitment outputs from the commitment transaction supplied to the pool transaction. And the trade result, as you can see, is settled in these two settlement outputs into settlements. The second to last output is our service commission output, and the last output is the transaction fee output. And now let me simulate this exact spend using the script wizard IDE. So I've simulated this pool transaction spend on the script wizard IDE. So script wizard IDE is a Bitcoin and Liquid script debugger tool for better simulation of scripts. You can see I selected Liquid tab script. I've imported the transaction template based on the inputs and outputs on this particular pool transaction. And if you compile the script, as you can see in the compile result, it gives you the script byte data, and you can see it matches 101 when you tap details. This whole big heavy script, right? And we are essentially simulating this spend on this online IDE. So our script is divided into three parts: header, body, and footer for better demonstration. So we'll start off with the header, of course, starting from the first line. But in the witness, we put some stack elements, right? The first item is the commitment input tweet key prefix. So as you see, guys, the last two inputs in our pool transaction, aka commitment inputs, are pay-to-tablet constructions, and the witness programs of pay-to-tablet constructions are the last 32 bytes of the tweet key, right? But the first byte, the prefix of the tweet key, is unknown, right, over introspection, and that is something we have to put in witness, which in our case was 2, right? And the following 6 stack elements are the commitment transaction in row hex in 6 settlements, right? This is the non-witness based serialization. We have to put this into witness because we want to essentially inspect the call data, right? And in order to do that, we need to unfortunately put the whole transaction base byte data, and we make sure that it matches the odd point, right, of commitment inputs that I'll show in a sec. But in these first lines, we make this cat. Each settlement is 80 bytes because it is a standardness relay limit. We had to put that in 6 settlements, and we kept them and swapped them, right? And then the end result is this whole base byte serialization, which is 418 bytes by standard, and O2, right, the tweet key prefix. The header is mostly based on hard-coded values. The first hard-coded value is the flag asset ID, right? Similar to what we did in the LP and token holder covenant, we encode the flag ID, flag asset, in our script for further use in the script. And the second item is a tab script mask. So tab script mask is a bit of a compressed version of the tab script content of our commitment inputs. We use this mask to construct the script within the script. And the third item is the point with an unknown discrete logarithm. The type script is always tweaked with this internal key with an unknown script logarithm. That is also something we have to hard code. And script tab leaf elements and script string tab tweak elements, we need to encode them for the inspection of tab script. And then we inspect the input index 0, which is flag covenant. We make sure that that equals to the hard-coded flag covenant, right? From the header, we just encode it. We make sure that these are the expected flag asset. Essentially, we are making sure that we are executing the right contract call in the right contract. And then we verify that we count an input index, which is 3. We inspect the number of inputs, make sure that is 6. The outputs is 8. This is a single slot spent, but in fact, this main covenant can be up to 33 slots. This is bounded by 33 for the current spec. This could improve over time or across specs. This is a must tree made of 32 slots, aka 32 leaves, right? Every leaf essentially accommodates that leaf number of slots, right? This is how we are tackling the concurrency issue. So you are calling the respective leaf spans based on how many concurrent slots exist in that period. But in this example, we are making a single slot spend. Think of that, we are spending the first slot index, the first leaf, right? We are calling the first leaf. And you obviously create a control block based on the spend, in fact, which we did. If you look at the spend, the control block points out to the first leaf spend, which is a single slot spent. Yeah, and these parameters could be, the numbers could be different in different slot versions, obviously, depending on how many slots you are executing. In the next 3 steps, we inspect LBTC liquidity from the third input index, right, this amount, and we send that into alt stack. In the next step, we inspect the token pool liquidity in the first input index, this amount, and in the next step we inspect LP pool value in the second input index, and we send that into also alt stack, and we send then the integer 0 to alt stack and the max 32-bit integer into alt stack for further use. And this is the end of header, and then the body begins. So the body is a varying size field in a script that accommodates these slots, right? In our case, we have only 1 slot, so our body consists of only 1 slot. So at the end of the slot, the body ends, right? And in the first lines, we fetch the commitment transaction base byte data, essentially this whole 418 byte data, and we make 7 new copies out of this. We compute the transaction ID, right? And make a copy and make sure that that equals to the add point, right, of the commitment inputs. So we make a hash of this. The result was apparently, you can see AAAA110, right? As you can see, our transaction ID. But that is in Little Endian though. But you can see that is, yeah, in Little Endian the correct transaction ID we're spending. Also this one, right, the commitment transaction we are spending. In the next steps, once we make sure that transaction ID matches our odd point, we also make sure that the commitment input odd point also matches the same transaction ID in a different vault index, of course, right? And then we enforce this size, which is standard, right? commitment transactions are standardized template, so they're always 418 byte in size. And then we do constrain commitment transaction version to 2. So we have this whole transaction base byte construction, right? And then we can make any data manipulation out of this. First thing we do is we make sure that the transaction version, the actual version, is 2, doing this splice opcodes. Then we do constrain the number of inputs, which is 2. Commitment inputs always have 2 inputs. And then we constrain first input to this input sig in this empty script sig with the following n seconds. We picked maximum n seconds because we wanna also mitigate front running to some extent. So in this case, when you create a contract call, you cannot practically bid for higher fees because you're opting out RBF. So this is a bit of a a mitigation, right, of front running. But anyhow, we do the same for the second funding input in the commitment transaction. We constrain the number of outputs to 4. Again, commitment outputs always have 4 outputs. The first output is again an op return. We make sure that is an op return with the 78 byte data push. We extract the call data, right? We can do data manipulation. We extract the call data within the op return. The first 32 byte is the flag asset ID. We parse that, then we parse the flag asset ID, and we make sure that the parsed flag asset ID from the call data matches our hard-coded target flag asset ID that we fetch, right, from the stack. In fact, let me see the stack execution line by line on the right side of the editor here. And then we parse the recipient pub key. The next 33 bytes is the following. Parsing the slippage tolerance, you can see, and then we parse the ordering phase, the last 4 bytes, convert that into a script num, which is 1. Oops. And then what we need to do next is we really need to construct the whole tab script of our commitment inputs. We need to do this because we want to make sure of the content of the commitment inputs to make sure that that is a standardized template. So we want to make sure, again, this is a standard script template. Again, as you remember, based on 2 paths, a timeout path and a success path. So if you want to transact with Bitmatrix, you have to comply covenant rules bit by bit, right? We don't really want bad things to happen here. So in order to construct this script content, right, we pick the TypeScript mask, as you remember, encoded in the header part, and we fill that mask essentially with two datas, right? The settlement pub key and the flag asset, right? And we do again some manipulation based on this TypeScript mask, and the end result is our TypeScript bytes, right? And as you can see, if I copy this, you can see this matches 101, our commitment input TypeScript content. And then based on this content, we calculate tab leaf by picking first the tab leaf / elements and doing this data manipulation, and the end result is tab leaf. And then based on the tab leaf and our internal discrete unknown discrete logarithm pub key, we compute tab tweak. So we have tab tweak, and then what we do next is we fetch the commitment input tweak key prefix from the witness, right? And then we inspect the commitment input witness program, right? And then we make sure that commitment input to witness program and 1 is equal, right? And we do a cat operation, essentially concatenating this prefix with the inspected witness program giving us the final 33-byte tweak key, right? Because tweak verify operation needs that full 33-byte tweak key. We fetch the hard-coded point, right, with this unknown discrete logarithm. So we have 3 inputs, right, that feeds tweak verify. So we end up with 3 inputs feeding the tweak verify, right? The point with an unknown discrete logarithm, the tap tweak result, and the full tweak key. And tweak verify succeeds, as you can see here, right? So we make sure of the content and the authenticity of the temp script that we constructed. What we do next is we compare the higher index, right? So this is Bitmatrix design is based on slots, and slots ordering is based on a fee market, right? So as you remember, you are bidding over a fee market to reserve these slots, and the more you fee, the highly ordered your slot ends up becoming, right? In the end order, right? And if you end up paying the same fee, slots are ordered lexicographically. So what we do next is we call the lower index ordering fee from the stack, which is apparently the max 32-bit integer, right? Because this is the first slot execution actually in and there is no upper index slot, right? And this is the max integer, therefore. And we get the total ordering fees, which is 0, right? We make a copy of ordering fees, and then we obtain the total ordering fees, right, by adding 1 to 0, which is 1. So this is the current final total ordering fees. And we send that to AltStack for further interpretation. Then what we do next is we make 2 copies of ordering fees. We make sure that current ordering fees is equal to 1 and greater than 1, sorry. And then what we do next is we compare the current ordering fees 1 and the upper index, the upper slot ordering fees. So as you can see, this our index fee is lower than the upper index. So this code block succeeds, right? We drop the 2 fees. But if our fees were equal, we had to enforce an lexicographical ordering. The code block we're not executing now, but essentially we inspect the current slot, supplies the first 8 bytes, inspect the higher index, right, or in fact lower index higher slot, out point, supplies the first 8 bytes, and compare these 64-bit integers, right? The ordering has to be based on lexicographical ordering. And in the next step, we have to construct the settlement output witness program. So what we do now is we create settlement outputs based on the standard pay-to-witness pubkey hash. But in a production scenario, we should do this custom pay-to-witness script in which we do enforce 1 block relative log time and check sig based on recipient pubkey. So as you remember, guys, every single input in a pool transaction signals 1 block relative log time, but we have to do the same for every single output in a pool transaction to avoid transaction pinning attacks, which would affect the replaceability nature of our covenant design. What we do next is we make sure the settlement output 1 is given to the calculated witness program and with the witness version 0, right? Making sure they're equal. We make sure that the first commitment input carries LBTC because regardless of the type of interaction, whether it's liquidity addition, removals, or swap, first commitment input always carry LBTC. And we make sure of that, right? And in the next step, we get from AltStack the total current ordering fees, LP token, and LBTC pool liquidity supplies, right? And then we make sure that flag covenant sequence 1, right, also equal to the commitment inputs, right? We are making sure every single input, including commitment inputs, have this end sequence 1. And then we make sure that settlement outputs, like the two settlement outputs, are equal, in fact, right? In the previous steps, we verify the settlement output 1, but we now make sure that settlement output 2 is equal to 1. And in the next step, we fetch method call the field we parsed from the call data, which is 1, right? Which is swap LBTC for token case. So this is the code block we're executing, right? We are making an LBTC to token swap. So this is the actual CPMM rules, right? We are starting to enforce now. So the first thing we need to do is we constrain commitment input to LBTC as well. In the previous steps, we did the same for a commitment input 1. In this case, both commitment input 1 and commitment input 2 carries LBTC, right? And then we inspect the values, right, of the two commitment inputs, and we add them together, right, giving us the total supplied LBTC amount. And we subtract from this amount the base fee and service commission and the ordering fees, actually, which makes apparently total 701, right? Essentially, we again subtract fees from the total supplied amount, ending up with the remaining available amount, right? We have some limits applied here, right? We make sure that that's greater than 1,000 sods. We here in this step calculate the 0.02 LP fee. We subtract the fee from the amount, right? We calculate the LBTC new pool amount by adding the previous pool amount that we've called from alt stack with the new available supply, right? So we need to do some precision downgrade. That is a bit of technical, but we need to downgrade precision because we're working with 64-bit integers. In fact, if we had a very high amount of tokens, right, supplied to pool, then that would overflow the operation. Hopefully soon we'll have ideally 128-bit operations that would not overflow the operation, but yeah, we have to do some downgrade to not overflow the operation for now. And then we make a copy of total LBTC pool supply, apply the same precision downgrade. We make a copy of total token pool supply, again apply this another precision downgrade, and we multiply the token pool supply and LBTC pool supply, which essentially gives us the constant value, right? And then we divide constant value, right, with the previous result. That gives us the new token supply. And we apply these precision downgrade. And when we subtract the new token supply with the old token supply, that gives us the amount of tokens user receives. And we subtract some 3 cents from this amount for some security reasons. And essentially that is the amount, right, a user has to receive if it passed the slippage final check, right? So we fetch the slippage limit, parse from call data, right? We make sure that if slippage limit is not overflow, then we constrain settlement outputs, right? The two settlement outputs to the exact amounts, right? We end up in two settlements. So essentially we divide that number with 2, and we distribute that to settlement outputs into settlements, right? And we update the new LBTC supply and the new token supply. But if the slippage is not overflow, what we do really is we divide the remaining supply into 2, right? And we distributed that number into 2 settlement outputs in 2 pieces, but this time making sure that the asset is LBTC. instead of token. And that is the end of the case, right? There is other cases obviously, but these blocks are not being executed because our case was the case 1, and that does not execute the case 2 and 3 and 4 if else blocks. So I'm passing these lines, and then the footer comes, right? So in the footer, what we do is we get total ordering fees, right, which is 1. This is a single slot span again, and the total ordering fees is by nature 1. We add total ordering fees with the replacement bandwidth that I'll outline in a few seconds. So there is this bandwidth thing that we have to pay to guarantee the replaceability, again, nature of the covenant design, aka the concurrent nature, which is a predetermined number. So we add that number, right, to total ordering fees, and then we get the fee output index and make 3 copies. And then we inspect the fee output value, right, and we constrain that output value to calculated fee. First we verify the fee output script pub key, which is an empty script, right? And this inspect script pub key does the shell of this empty script, and we verify that. And then we verify the fee output asset, make sure that it is LBTC type, and we verify the fee service output witness program, verify the service fee output asset. This is the Bitmatrix team address, and the fee output asset is obviously LBTC. Then we get pull LP supply latest state, and we make sure that the LP holder covenant final state equals to that amount, right? So we inspect the second output index amount, and we make sure that from the alt stack, LP pull supply is constrained to that. And we do the same for the token, right? We get the token pull supply from the alt stack, and we constrain that to the first output, right, amount. And the same goes for the LBTC, right? We get the final LBTC pull supply amount from alt stack, and we constrain that to the third output index amount. And then the next steps are the constraining flag covenant witness program. Right, so what this says is the index 0 input and index 0 output witness programs should be equal. So this is a cross input output covenant. We want to make sure that, right, output script pub keys are the same as inputs script pub keys. Same for the token holder covenant, same for the LP holder covenant, same for the main covenant, right? We want to make sure that these script pub keys are the same across inputs and outputs, right? And then what we do is we constrain the flag holder covenant asset, which is the flag asset. The token holder covenant holds the token asset, LP holder covenant holds the LP asset, LBTC holder covenant holds the LBTC asset. Then we constrain the transaction version to 2 and lock time to 0. So I've mentioned the bandwidth, right, earlier in the simulation. So the Bitmatrix design is concurrent by design again. And we guarantee that by introducing this replaceability logic, right? So in Bitmatrix, multiple users can, interact with the same pool, right? So you can end up with multiple slot spans, right? And we want to make sure that the higher index, like higher slot spans, are always replaced by the lower slot index by paying some bandwidth, right? So the one of the rules of BIP 125 says is that the replacement transaction must pay its own bandwidth for the replacement, right? And that is based on the v byte length of the replacement transaction multiplied by with the minimum relay fee. And by doing the calculations, each leaf span has to pay a certain amount of bandwidth. So imagine a scenario, right? We are having a honest node and an evil node. The honest node does a 2-leaf span and the evil node does a 1-leaf span. So there is actually 2 transactions happening, 2 trades happening in a transaction. So this is a 2-leaf span, right? In fact, a 2-slot span, but an evil node ignores one of these slots, right? And in that case, evil node and honest node propagates their own version. Again, it goes on and on up until, right, one of these nodes, right, one of these red nodes recognize the new version, right, the 2-leaf span version, because it pays its own bandwidth, and essentially the honest version ends up winning. So the highest index pool transaction is always replaced with the lowest or lower index pool transaction. So that pretty much sums up everything, guys. So that this will hopefully give you guys a better understanding how things work. So I'm looking forward to your feedback. Thank you.